Okay, today we are diving into a really unique argument. You gotta admit, the title alone is a head turner. Socialism violates the second law of thermodynamics. I mean, it's a huge claim, right? It tries to connect physics, politics, and even law. So the big question is, how on earth does the author even begin to build that case? Well, let's find out. So, right out of the gate, the author hits us with this incredibly bold statement. Now, just as a quick refresher, the second law of thermodynamics is basically the idea that everything in the universe tends towards disorder, or what scientists call entropy. Things get messy over time. So the author is arguing that socialism itself, as a system, actually goes against this fundamental universal law. That's a massive assertion, and it immediately makes you wonder.
And yeah, that is the million-dollar question, isn't it? That's exactly what we're going to unpack here. So let's follow the author's chain of logic step by step and see exactly how they try to build this bridge between the world of physics and, well, the world of paperwork.
So the whole argument starts not with giant economies or nations, but with something much, much smaller. Something many of us have probably experienced, the committee meeting. The author wants us to start by looking at how bureaucracies work, but through the lens of physics. Okay, so here's the core idea. I want you to picture a committee room. In physics, that's what's called a closed system. It can exchange energy, like heat, with the outside world, but not matter. In this analogy, the people, they're the matter. They're stuck in the room. And the energy, well, that's all the heated debate and arguments happening inside. To kind of ground this idea in political theory, the author brings in this quote from the economist Ludwig von Mises. The whole premise here is that if socialism fundamentally relies on bureaucracy, then to understand the whole system, you first have to understand the fundamental nature of its building blocks, things like committees. And this is where it gets really clever and, honestly, kind of funny. The author literally translates famous scientific equations into these satirical observations about committees. For example, delta E equals Q becomes committees absorb heat but never convert it into results. Perfect. My personal favorite is Q equals T, delta S, which gets translated to heated discussions breed disorder, not decisions. It's a really cynical but sharp way of framing bureaucratic inefficiency not as a flaw, but as a law of nature. So this idea then gets built out into a full-blown visual model. The author isn't just sticking with clever metaphors, they actually propose a specific model from physical chemistry to describe what they call the mote effect. So what exactly is the mote effect? Well, it's the author's way of creating a picture of committee in action. Imagine the decision you're trying to make is a castle in the middle. The committee's endless debates and discussions create this moat of an action all around it, making that goal impossible to reach. And here you can actually see it. On the left, you've got the conceptual drawing, that pillar in the middle is the goal, and it's surrounded by that dip, that moat of inaction. Then, on the right, you see the actual plot generated by the author's physical chemistry equations, which was specifically designed to mathematically recreate that exact shape. But here's where things get fascinatingly specific. This entire model operates at a scale of 55 nanometers. Now, to put that into perspective for you, a single human hair is about 80,000 nanometers wide. So we are talking about a scale that is truly deeply submicroscopic. And it's at this tiny level that the author is trying to model the behavior of a bunch of people sitting in a meeting. Now, you might think this is the big conclusion, but then the author does something I really respect. They find a massive hole in their own theory, a fundamental problem with how the model was first designed. So, what went wrong? Well, it was the material they chose. The model was based on water in its gas phase, so steam. But at that ridiculously tiny 55 nanometer scale, and at regular room temperature, the author realized the water molecules would be so crammed together, they'd just be in a constant state of collision, so instead of acting like a gas, they'd act more like a solid. And for that reason, the author themselves flat out declares it a failure of the model. So, where do you go when your own model fails? Well, this is where the argument takes its final, and maybe its most abstract turn. The author pivots away from physical chemistry and moves into fluid mechanics, and believe it or not, all the way to law. So instead of water, the author suggests a new model based on sand. Now, why sand? Well, because the way sand behaves, its fluid mechanics, can be modeled pretty consistently whether you're looking at it on a microscopic scale or a huge macroscopic one. It avoids the problem that the water model ran into. Now, to bridge this conceptual gap, the author pulls in a quote from, of all places, Frank Herbert's sci-fi classic, Dune. The quote connects the flow of sand to the flow of a river. And this isn't just some literary flair. This is the crucial link that lets the author jump from the physics of tiny particles to the much larger laws that govern waterways.
Okay, so let's just pause and trace this final, absolutely wild chain of logic. 1. The water model fails. 2. It gets replaced by a sand model. 3. The dune quote is used to connect the flow of sand to the flow of rivers. This brings in something called centerline theory, which is used to map rivers. And 4, here's the final leap, that centerline concept, according to the author, connects directly to federal admiralty jurisdiction, which is basically the law of the sea.
And this is it. This is a grand conclusion of this whole winding intellectual journey. The author is asserting that by following this chain of logic, all the way from a committee meeting to a failed water model to sand to rivers to legal theory, they've somehow proven that admiralty jurisdiction isn't just for the sea. It's a universal law without limitation that extends to all time and space. So, what are we supposed to make of all this? The author actually gives us a way to think about it in their own introduction by asking if any field of science is a truly unified theory, or if it's just a studied bias. And that is a fascinating question to end on, right? It leaves us to wonder whether this whole complex argument is a groundbreaking connection between totally different fields, or maybe just a brilliant example of finding the exact pattern you were looking for all along.